Asynchronous counters are constructed from the chain of JK flip-flops, each of which operates in the counting mode. The output signal of each flip-flop works as an input signal for the next trigger. Therefore, all bits of the asynchronous counter are switched sequentially, one after another, starting with the lowest order and ending with the highest order. Each next bit switches with a delay relative to the previous one, that is, asynchronously, not simultaneously with the input signal and other bits. The more bits a counter has, the more time it takes to complete switching of all bits. This imposes severe restrictions on the input signal frequency. If the number of the counter bits is increased, for example, by half, the maximum permissible frequency of this input signal will be automatically reduced by half. There are not so many asynchronous counters in standard series of digital circuits. For example, a 4-bit IE2 binary decimal counter, 4-bit IE5 binary counter, and an 8-bit IE19 binary counter. All asynchronous counters work on the negative edge of the S input signal. In schemes counter, outputs are indicated 0, 1, 2, 3 as the numbers of output bits of the binary code, or 1, 2, 4, 8 as the weight of each bit of binary code. It is very simple to combine counters to increase the bit. You need to connect output 8 of the previous counter, issuing lower order bits, to C1 input of the next counter, issuing high order bits. However, when performing the connection, one must bear in mind every new bit added increases the overall switch delay of the counter. A multi-bit asynchronous counter can become unacceptably slow. Asynchronous counters are mainly applied for construction of various frequency dividers, that is, devices issuing an output signal with a frequency that is several times lower than the frequency of the input signal. When frequency dividers are constructed, sometimes output signal frequency is not the only important thing. Signal form, duty cycle, that is, the ratio of pulse repetition period to the duration of these pulses, are also important. In such cases, most the meander is often required. It is a digital signal with a duty ratio equal to 2. The simplest example of frequency divider issuing a meander is implemented using one IE2 counter. Sometimes input signal frequency needs to be divided into an arbitrary number of times. In this case, by introducing feedback, we can organize counter reset when it reaches the required code. Controlled frequency dividers can also be constructed on asynchronous counters. These are dividers with an output frequency determined by a control code. Asynchronous counters are used not only for frequency dividers. In cases where high performance is not required, when transients at the outputs of the corner are also not that important, asynchronous counters might as well replace faster synchronous counters.